Hello everyone, I'm Noof or Wes, one of a cast of many on the CHERI Capability Architecture project. I'm going to present Cornucopia, our fully elaborated design for temporal safety of CHERI-aware NICS user space programs heaps. That's a bit of a mouthful, so we'll get there in stages. First, I'll say what we mean by memory safety. Then, a quick review of some earlier work, the CHERI architecture, what it looks like to port a NICS to it, and a surprisingly simple revocation sweep strategy for temporal safety. Foundations in place will implement that strategy in the NICS kernel and modify a malloc to use it. We'll see that it is straightforward to make our implementation do most of its work concurrently with the application. Last, we'll look at measurements we took to assess correctness and performance. Memory safety is a difficult term to define precisely, and opinions differ, but we take it to have at least three aspects. First, memory safety requires that we have notions of provenance and integrity of pointers. Pointers come only from other pointers or more trusted components, such as the kernel, and pointers are immune from bit-level tampering. Next, we must be able to carve memory up into objects that have defined location and size. We may access an object only if we have a pointer to it, and having a pointer to an object does not give us access to neighboring objects. And last, objects may have bounded lifetime. Newly constructed objects are distinct entities, even if they occupy reused memory. We must not hold a reference to an object before it is created, and references must cease to be useful after memory is reallocated for another object. Conceptually, holding a pointer confers authority to access memory, and there is a natural correspondence between the safety properties just outlined and authorization. Pointer integrity and provenance mirrors the unforgeability of authority. Spatial safety reflects limited authorization, and temporal safety corresponds to revocation of authority. Capability systems use explicit bearer tokens to capture authority. In these systems, capability revocation is, like temporal safety in C, generally considered hard to implement without sacrificing performance. CHERI is a capability processor architecture designed to run C programs and yet enforce aspects of memory safety within the instruction set itself. CHERI capabilities are 128-bit packed structures, pairing a traditional 64-bit integer address with upper and lower bounds. Moving the address out of bounds and dereferencing will trap rather than access memory. By distinguishing between integers and references at the ISA level, we can begin to enforce provenance. Capabilities can be copied and manipulated using dedicated instructions, but directly manipulating the bit representation of a capability turns it into data by clearing an out-of-band tag bit, making it no longer usable as a reference to memory. The CHERI ISA does not offer mechanisms for setting the tag bit or enlarging the bounds of a capability without already holding a still-tagged capability that would encompass the result. Thus, CHERI can readily enforce provenance and spatial aspects of memory safety. CHERI composes with host instruction set architectures. Cornucopia was implemented atop the CHERI MIPS architecture, but our work will port to CHERI RISC-V and to ARM's experimental Morello. Using CHERI's enforcement possibilities required many but modest changes to runtime and system software. The C and C++ compiler, operating system kernel, and runtime libraries, notably including the heap allocator, all had to be taught to use the CHERI protection mechanisms. The net result is a new capability-based NICS ABI for spatially safe user space programs. For our purposes, a key point is that malloc returns pointers with bounds set to the allocated region, and these pointers are the only way to access that memory from outside the allocator, which we take as part of the trusted computing base. CHERI and CheriABI address integrity and spatial protection, but CHERI capabilities are self-contained objects. Like integer pointers in traditional C implementations, CHERI capabilities are prolifically copied by CheriABI programs. By design, CHERI does not require indirection to interpret its capabilities, and the conceptual provenance tree is compressed to a single tag bit. These decisions increase performance and microarchitectural familiarity, but challenge revocation. In short, applications can still retain copies of capabilities handed to free, and so CheriABI risks not mitigating a large, often exploited class of vulnerabilities. We are after defenses sufficiently performant that they can be always on, not just when debugging or testing. We focus on the case of a well-intentioned but buggy application exposed to an adversary with direct access to malloc and free and to memory it has allocated, but we do not go so far as to permit arbitrary code execution. Roughly, our adversary is something like JavaScript running in a web browser sandbox. The adversary wins if a capability it obtains from malloc comes to point to another object's memory. We must eliminate temporal aliasing of objects, what might be called use after reallocation, although we may permit some use after free so long as the memory has not yet been repurposed. That is, Access to free memory might indefinitely continue to see the old object. Attacks rely on aliasing, not merely use after free, so this weaker defense still suffices. Leaking memory on free satisfies our requirements, but we rule it out. In prior work, we assessed the feasibility of combining delayed reuse of memory with precise detection and removal of capabilities to free memory. The CheriVoke algorithm modifies heap allocators to collect freed memory in a quarantine state rather than immediately offer it for reuse. Once quarantine hits some size threshold, the application is paused and all memory is swept for capabilities. Every capability found is assessed to determine if it points into quarantine, and if so, it is replaced with a trapping value, such as null. The quarantine, in principle, is any subset of the heap. For maximum flexibility, CheriVoke proposed the use of a shadow bitmap with a simple function to translate a pointer's target to corresponding shadow bit. The allocator may keep quarantined regions in list form, but the sweep uses constant time probes of the bitmap. So all told, what does this look like? An application makes allocation requests from malloc and propagates the returned pointer to other locations on the heap or on the stack, into registers, or even into the kernel itself. An application might retain references to a heap object after freeing it, and the underlying risk, absent enforced temporal safety, is that the allocator may create a new overlapping object. Instead, CheriVoke or Cornucopia's allocator quarantines the free space and sets bits in the shadow. Cornucopia takes the shadow to be a contiguous block of virtual address space corresponding to the entirety of user memory. The allocator obtains access to the shadow via a system call. Eventually, the allocator requests that the kernel sweep memory and ensure that no capabilities pointing into quarantine remain. When the sweep is finished, the memory is safe to reissue, and the allocator clears the shadow bits and puts memory back in its free list. As said, CHERI and CheriABI seemingly have no overt support for temporal safety or capability revocation, thus the need to sweep memory. However, we find that it is an effective substrate for this sweep, especially with some modest tweaking. At its core, revocation requires that we be able to tell with certainty what is and is not a capability. CHERI tag bits answer this question precisely and without any extra data structure lookups. CheriVoke proposed, and we have added, a cload tags instruction in CHERI MIPS so that we can read an entire cache line's worth of tags at once before we pull the line itself into cache. This lets us skip lines that do not have capabilities without perturbing caches or going to DRAM for the line contents. For those lines that do contain capabilities, we have added way-restricted prefetching operations to our cache fabric and have unrolled the revocation loop to overlap prefetching with revocation. At larger scope, we have repurposed a long-standing protection feature in CHERI MIPS, where pages can be marked as raising traps on tagged capability stores. In Cornucopia, the kernel observes when pages come to hold their first capability. To first approximation, the trap handler updates metadata and allows all subsequent capability stores to go ahead without traps. So, with those ingredients, our initial implementation of Cornucopia's revocation sweep begins with a barrier to suspend all other threads in a program. With the world stopped, we examine every capability to which the application has access. The bulk of the time and effort goes into examining application memory. Here, we take advantage of being in the kernel to quickly skip over regions of the address space that are unmapped or that are forbidden from containing capabilities. Within mapped regions, we use capability store tracking to skip over pages not containing capabilities. And within pages, we use cload tags to skip over cache lines. When we find a capability, we probe the bitmap and, if its target is quarantined, replace it with a trapping value, such as null. Besides memory, we must examine some additional state. The thread register files, conveniently stored as trap frames, must be examined, as must any other place where the kernel stores capabilities for userland's use. Each subsystem requires a little bit of specialized code. With all state examined, any other threads are resumed, and control is returned to user space. While we do, indeed, visit all capability-bearing application memory, like a GC, it's worth emphasizing that our sweep is much friendlier to caches. We stride predictably within pages rather than chasing pointers in a graph walk, and, while bitmap probes are random, the shadow bitmap is quite small. The requirement that we suspend the application for the entirety of the revocation sweep is not stellar. Memory is big, and even with our architectural assists, sweeping takes a long while. Instead, we borrow a key insight from GCs and virtual machine migration, take many passes, each hopefully reducing the work required later. For us, that means distinguishing pages that have already had all of their capabilities checked from those that have had new ones stored since last visit. We achieve this by resetting visited pages to trap on capability stores, just as we do to track capability flow to pages without capabilities. This trapping behavior is not architecturally tied to the presence or absence of capabilities, it's just a behavior under system software control, and so we can repurpose it. The net result is that we can split revocation sweeps into two phases. In the first phase, we visit all capability-bearing pages concurrently with the application, being careful that any application's store of a capability to the page will cause us to revisit it later. In the second phase, we stop the world and visit all pages modified since their last visit. Because the set of memory in quarantine changes over time, revocation must visit all capability-bearing pages each time, regardless of modification. To check that Cornucopia does the right thing, we use the Juliet test suite's corpora of double-free and use-after-free examples. As expected, all tests exhibited violation of temporal safety without Cornucopia. With Cornucopia, all tests aborted, so long as we set the quarantine size to 0, triggering revocation immediately on every free, and also adjusted free to abort on, rather than silently ignore, double free. While these are not our usual operating parameters, this nevertheless demonstrates efficacy of our revocation sweeps. On CHERI-compatible Spec CPU 2006 integer benchmarks, Cornucopia's single-threaded implementation achieved a geomean of 5.8% overhead. With a second thread and a dual-core CPU, that dropped to less than 2%. When offloading, the world was generally stopped only 10 to 20% of the single-threaded sweep time. Notably, applications were unmodified relative to their CheriABI ports. We ran them under a Cornucopia supporting kernel and used LD preload to shim a replacement malloc over libcs. In terms of memory occupancy overheads, generally Cornucopia manages to hold to its a priori chosen target of 33%. When using a second thread and offloading, Cornucopia overshoots a bit due to allocations made during the concurrent sweep, which can be satisfied only by growing the heap. The bzip2 and sjang workloads do not really avail themselves of malloc and so do not rise to threshold, while Hammer and OmnetPP appear to go through distinct phases and cause our underlying malloc implementation to not reuse memory as aggressively as one might wish. Beyond cycle times and memory occupancy, a very important, if underreported, metric is memory traffic overhead. Most of the benchmarks tested showed very modest traffic overheads of 0 to 5%, but workloads that thrashed the allocators showed 15 to 30% overhead when using the inline Cornucopia revoker. Switching to concurrent revocation raised those further to 30 to 45% as pages were revisited and the concurrent pass itself necessarily increased cache contention. Interestingly, for these thrashing workloads, we see that merely quarantining accounts for somewhere between 5 and 10% of the overhead. This suggests that we may be intermixing objects of different lifetimes within cache lines, decreasing the utility of our caches. If you're still curious for more, our paper goes into much more detail. We include discussion of 3 different user space components we developed and considered, a deeper analysis of where revocation incurs expense, and several considerations for future work and deployment of Cornucopia. We simulated releasing quarantined pages back to the operating system to reduce the need for sweeping. And last, the paper details mechanisms for secure and efficient operation of multiple allocators within a single program. We believe that sweeping revocation is within engineering effort of practicality, and that there are some relatively straightforward steps we can make to lower the overheads reported here. We can confirm the observation made by Bogo. While temporal safety has historically seemed expensive to achieve, being able to leverage spatial safety brings the costs down. We are pursuing a new sweeping strategy that should address our worst overheads, and, simultaneously, we are aiming to land in mainline CheriBSD, so that, soon, every CheriABI program can enjoy heap temporal safety. And with that, I'll take questions.